Hi there, so today we're having a look at 14.5 direct proportion. The objectives today then to be able to solve direct proportion problems and to interpret graphs showing direct proportion. Before we start, as always, we're just going to check our prior knowledge. So to be able to complete this lesson, you should be able to simplify ratio in the form 1 to n or n to 1. Such as if we had 4 to 5 and we wanted in the form 1 to n, it would become 1 to 1.25. Or if we had 5 to 8 and we wanted it in the form n to 1, it would be 0.625 to 1. We should also be able to rearrange formulae for a specific letter. So if we were given r equals 5s and we want that rearranged so that we can find the value of s, we would divide both sides by 5, leaving us with s equals r divided by 5. To complete this lesson, you will also need to have some paper or a maths book, a pen or a pencil, and a calculator. It doesn't need to be specifically scientific for this one, but hopefully most of you have got your scientific calculator handy. Okay, so before we start then, let's just do a quick ratio recap. So checking that we can change our ratios to the form 1 to n. So if we wanted in the form 1 to n, what that's telling us is that what we want is underneath R7 here, we want to have the value of 1. So let's do that. Now to get from 7 to 1, we need to divide both sides by 7. 7 divided by 7 would give us 1. So if we divide by 7, we get 1. And if we do the same to the other side, dividing by 7, 42 divided by 7 gives us 6. So we get 1 to 6. So remember, when we're simplifying ratio, whatever we do to one side, we do to the other. And if we want them in the form 1 to n, we're going to put a 1 under the first side and work out what do we divide by to get from our original value down to 1. Okay, there are 2 more there then for you to have a go at. So pause the video, have a go yourself now. Okay, so for our first one then, if we want the 1 to be under the number 4, we're going to need to divide both sides by 4, which gives us 1 to 3. And if we want, for the last one, the 1 to be under the number 10, we're going to divide both sides by 10, which gives us 1 to 2.5. So with these, we can have decimals or fractions, if you prefer, in your ratios. Let's just check we can go the other way then. So if we want them in the form n to 1. So if I want it in the form n to 1, that means that my 1 now needs to go underneath my 9 here, so the 1 is going on this side. Okay, so we'll put our 1 there under the 9. To get from 9 to 1, we're going to divide by 9. We do the same to the other side. 27 divided by 9 is 3, and we get 3 to 1. So again, 2 more there for you to have a go at then. So pause the video, have a go at simplifying those in the ratio of n to 1. Okay, so this time then we want the 1 underneath the 8, so we're going to divide both sides by 8, giving us 2 to 1. And for the last one, we want the 1 underneath the 28, so we're going to divide both sides by 28, and we get 2.25 to 1. Make sure you're happy with simplifying those in that form 1 to n and n to 1 before you move on. We're going to be using that to help us with our direct proportion today. Okay, so direct proportion then. Direct proportion is when 2 quantities increase or decrease at the same rate. So either they both get bigger at the same rate or they both get smaller at the same rate. So, for example, then the speed that a car travels is directly proportional to the distance that it covers. So if it doubles its speed, it will double the distance it travels in the same amount of time. If it were to half its speed, it would cover half the distance in the same time. And if it were at rest, it wouldn't cover any distance. So if the speed is 0, the distance covered is 0. So in previous lessons, we've looked at speed, distance and time. So you should be quite familiar with that. Another good example then is when we're exchanging money from one currency to another. So if we know that £8 is worth 13 euros, we need to work out what the exchange rate is. Okay, so we were told £8 is worth 13 euros. So we need to work out, well, what are we going to multiply 8 by to get to 13? Now to do that, we do the opposite. We do 13 divided by 8. And that gives us 1.625. So £8 times 1.625 means we have 13 euros. Now, once we know that exchange rate, we can use it to convert any amount of pounds into euros. So how many euros would we get for £2? So if we have £2 and we multiply it by the 1.625, our exchange rate, then we would get 3.25 euros. So when we're talking about money, we call that multiplier an exchange rate, but usually for everything else, we call it the constant of proportionality. Bit of a long word there, bit of a mouthful, but we're going to start calling it the constant of proportionality. So it's what we're going to multiply one value by to make sure that we're going in the same ratio. Okay. So we're going to learn a few new symbols then, a few new mathematical symbols and some new equations. So when we've got two quantities, y and x, are directly proportional to each other, we link them with the symbol for proportionality. So this symbol for proportionality then, this one here, okay, we'll get used to seeing that. We're going to be using that one today. So we write it then as y is proportional to x. So again, this symbol here is telling me y is proportional to x. That's what that's telling us. Now, as well as writing it as a proportion statement, we can also write it as an equation. So we've got y is equal to kx. Now this letter k is our constant of proportionality. So that was our value, our exchange rate when we did it with money, but it's called the constant of proportionality. It's what we're going to multiply x by to find a value of y. So if we relate that then to our exchanging pounds and euros, that was the question we had just now. So to get from pounds to euros, we worked out our exchange rate was 1.625. So that's our constant of proportionality, 1.625. So if we turn that into an equation then, if I want to know the number of euros, euros is proportional to pounds. So my euros is equal to my constant of proportionality, my exchange rate, 1.625, times the number of pounds. So this is our formula. Once we have this formula, we can work out any other value we like from there. So for example, if I had £10, I would do 1.625 times 10, giving me 16.25 euros. If I had £80, I would do 1.625 times 80, which will give me 130 euros. So you can see the 1.625, the constant, is called a constant because it stays the same all of the time. Okay, our variables are the amount of pounds that we have. So we've changed from £10 to £80 to find out how many euros we would get. So what we're going to do in this lesson, we're going to practice finding that constant of proportionality and then putting that into a formula to be able to use to find other values. So let's have a look then in a context you should be familiar with. So a spring stretches when a weight is attached to the end of it. The amount that the spring stretches by x, so that's our distance, is directly proportional to the weight attached to it, F. So remember, F is our weight. A weight of 10 newtons, so 10N stands for 10 newtons, is attached to the spring and it stretches 2 centimeters. Write a formula in terms of X and F. Okay, so we're going to go through this step by step. I would suggest you write down the different steps as we go, and then you'll be able to use those to help you with questions later. So our first step then is to write our proportionality statement. So we've started with X is proportional to F. So the distance is proportional to the amount of weight. As one gets bigger, the other gets bigger. As one gets smaller, the other gets smaller. We'll turn that into an equation. To change it into an equation, we're going to put X equals KF. So remember, we're multiplying because as one gets bigger, the other is going to get bigger. So by multiplying something, it's going to make it bigger. Once we've got that, we're going to substitute in the two values of x and f that we were told in the question. So we were told that f was 10 and x is 2. So we make sure we substitute them into the right places. So again, over here then, this is our x value here. So we've put the 2 in place of x. And our f value was 10. So kf means k times f. So I put back in the multiplication symbol there as well. Okay, next step then is to rearrange the equation to find k. So to get rid of a times 10 from both sides, I'm going to divide both sides by 10, which means that k is 0.2. So we now have our value of k. Finally then, once we know the value of k, we're going to substitute it back into our original formula up there. And we get x is 0.2f. So that there is our final formula then here. Okay, so we've got our formula, x equals 0.2f. So if I want to find the length it stretches, I would do 0.2 times the number of weight I put on it. If I want to find out what weight to put on to stretch a certain amount, I rearrange it for f, and I can work that out. We're going to go on to do that a little bit later. So first of all, we're going to practice these steps then. So make sure you've got all of those steps written down. We're going to practice those, going through the steps to find the value of k and then putting it into our formula. Okay, so it's your turn then. So you can pause the video, have a go, make sure you follow all the steps through carefully. So writing a statement, then an equation, substituting in the values, rearranging the equation to find the value of k, and substituting it back into the formula. Okay, let's talk through these ones then. So let's start off with our statement of proportionality. So x is proportional to t, which means x equals k times t. We substitute in our values of x and t, so make sure we get those the right way round. So 4 equals k times 5. Rearrange to find k, so we need to divide both sides by 5. And 4 divided by 5 is 0.8. So we found the value of k as 0.8, and we put that back in to our original formula. So x is 0.8t, and we now know the relationship between x and t. Our second one then, so we've got r and s this time. So again, start with our statement and then turn it into a formula. Substitute in the values of r and s. Divide both sides by 5 so that we can find k, which means that k is 1.6. And finally, put that back into the original formula, which gives us r equals 1.6s. The last one then, we're back to euros and pounds. So euros are proportional to pounds, so euros equals k times pounds. We're told that €1 is £0.80, so we're going to make sure we put those in the right place. So €1 is equal to k times 0.80. Again, divide both sides this time by 0.80, which gives us k as 1.25. And we substitute it back in. So in this case, the exchange rate here is 1.25. So 1.25 times the number of pounds will give us our number of euros. Okay, make sure you're happy with those before we move on. So this is the first step whenever we're doing a direct proportion question. We need to find the value of k and then find our formula. Okay, so going back to our spring then, so in our spring we were told our formula then was x equals 0.2f. Now we have that formula, we can use it to help us to answer some questions. All right, so our first question then is how much would the string stretch by if a weight of 35 newtons is attached? So if we start with our formula, 35 newtons, then that's the letter F, so we're going to substitute F for 35. So X is 0.2 times 35, which means X would be 7 centimetres. So if we applied 35 newtons to the spring, it would stretch 7 centimetres. So we're just substituting into our appropriate formula that we found. Next then, there we are. What weight would stretch the spring by 12 centimetres? So this time then we'll start again with our formula. X is now 12, so we're going to replace the X with 12. So 12 is equal to 0.2 F. Now we want to find F, so to get F on its own, we're going to have to divide both sides by 0.2. 12 divided by 0.2 gives us 60 newtons. So sometimes we can just put things straight into the formula, sometimes we need to rearrange the formula for the value that we want. Okay, our next question then. What weight would stretch the spring by 2 meters? Now we need to be a little bit careful here. Remember, we've been using centimeters, so X was in centimeters and they've now given us 2 meters. So to put that in as a value of X, we're going to have to change it to centimeters first. Okay, so 2 meters is 200 centimeters, so X is 200. Again, divide both sides by 0.2 to find F. And F would be 1,000 newtons. Finally then, can you see any problems with the last question? So a chance to just reflect on that last question, think about what we've talked about in terms of the weight and the length of our spring. I'm not going to give you the answers for that, I just want you to have a think about any things there that you think might be an issue with that last question. Okay, so we're going to have a go now at some exam questions. So with choice now, you can either pause the video and have a go at these first on your own, see how you do, and then watch us go through it, or you can work through it with me. So I'm going to have a look at 3 different questions on direct proportion. They're all structured slightly differently, but they are all from recent exam papers. Okay, so let's have a look at the first one then. So the first one here then, a ball is dropped from a tower. After t seconds, the ball has fallen a distance of x meters. X is directly proportional. Now, this is important to note. Look, x is directly proportional to t squared this time. Okay, so not just to t squared. T is 2, x is 19.6. Find an equation connecting x and t. So our first step then is to find our equation. So let's start with our proportion statement. So we have x is directly proportional to t squared. Okay, so we turn that into an equation. So x equals kt squared. So we've multiplied by our constant k. We're going to substitute in our 2 values. So we know then that x is 19.6 and that's equal to k multiplied by t, which was 2, and it's squared. So we need to work that bit out. So 19.6 equals k times 2 squared, which is 4. Remember, we want the value of k, so we're going to divide both sides by 4. So we divide by 4 to give us the value of k. Now we might need to use our calculator here for a second. So 19.6 divided by 4, that gives me 4.9. So k is equal to 4.9, and we're going to put that back in to our equation up here. So x is equal to 4.9 t squared. Okay, so that's our answer for part A. Part B then, find the value of x when t equals 3. So we're going to take our formula. So we said x is equal to 4.9, and we're going to multiply it. T was 3. so by 3 squared. So I'm going to do 4.9 multiplied by 3 squared, which gives us 44.1. Okay, so that's our value of x, and that was in meters. We then asked them for part C to find how long the ball takes to fall 10 meters. So our x value then this time is 10. Okay, so that's equal to 4.9 t squared. Now we just want t, remember, so first step, divide both sides by 4.9. That's going to give me t squared. So if I do 10 divided by 4.9, we get a nice long number there. So we get 2.0408, etc. is equal to t squared. So I'm keeping the long number in my calculator. I've just written down at least 4 decimal places. Now remember, we just want t, so we're going to need to square root that value, t.0408, etc. will give us the value of t. So I'm square rooting the answer that I've stored in my calculator, and then we can find our value for t. So t is equal to 1.4285, etc. Now again, want to give it to a reasonable degree of accuracy. We've been talking about time in seconds, so 1.4 seconds would be appropriate. Okay. All right, so let's have a look at the second question then. So our second question, a particle moves from rest and the speed of the particle is v meters per second. When it's moved a distance of x meters, v is proportional to the square root of x. So again, really careful here. We're not just doing it to x, we're doing it to the square root of x. When v equals 8, x equals 25, find the speed of the object when it has moved a distance of 56.25 meters. So in this case, they haven't scaffolded it like they did the last question. They didn't ask us to find the equation and then use it. They're just simply giving us the question, but we still need to follow those same steps. We still need to find our equation first before we'll be able to use it to find this distance that it's moved. So remember, they'll always give us our 2 initial values, and then they're asking us to use a second value afterwards. So let's start off again with our statement. So this time it said that v is proportional to the square root of x. So therefore v is equal to k square root x. So remember, we change our statement into an equation, change it to an equal sign, and we're going to multiply by our constant because it's direct proportion. So as one gets bigger, the other's getting bigger. Let's substitute in our values. So v equals 8. And we've got k multiplied by the square root of 25. Okay, so let's sort that bit out then. So the square root of 25 is 5. So we need to divide both sides by 5 to give us the value of k. Now 8 divided by 5 gives us 1.6. So our value of k is 1.6. We substitute that back in to our original equation. V equals 1.6 root x. So we've now got our equation. We can use that to help us to answer this question. So we want to find the speed when the object has moved a distance of 56.25. So x, remember, is 56.25 this time. So v is equal to 1.6 times the square root of 56.25, and we're going to put that into our calculator. 1.6 times the square root of 56.25, and that gives us an answer of 12 exactly, and our unit meters per second. So although it didn't ask us to find a formula in the question, until we found that formula, we can't use it to answer our question. Okay, next question then. So again, your choice, you can pause and have a go yourself, or you can work through it with me. So a car uses 3 litres of petrol when it travels 50 kilometres. Work out the amount of petrol the car uses when it travels 125 kilometres, and work out the distance the car travels when it uses 5.7 litres. So in this question, a very unstructured question, it doesn't mention direct proportion at all. It doesn't mention any sort of proportion, but we should recognise that it's direct proportion because we know the further we travel, the more petrol we will need to use. So as the distance goes up, the amount of petrol goes up. So with these sorts of questions at the highest level, they're not going to mention proportion in it. You need to be able to work that bit out. So again, to start then, we need to write our statement. So it uses litres of petrol. I'm going to call litres of petrol L, and we're going to say that's proportional to the distance it travels. So I'm going to call distance D. So you can use whichever letters you want to for this, but obviously try and make sure that it's obvious which ones you're doing. Okay, so that means L then is proportional to KD. If I use 3 litres, sorry, that should be an equal sign there, that should equal K times the distance we've travelled, which was 50 kilometres. So we need to divide both sides by 50. So 3 divided by 50 is going to give me K. So 3 divided by 50 is 0.06. 0.06 is K, and I'm going to put that back in to my original equation there. So L is equal to 0.06 D. So we're swapping out K for our 0.06. All right, now I've got my formula, I can go back to answering the question and say part A. We want to work out the amount of petrol when we travel 125 kilometres. So the number of litres we need, 0.06 multiplied by 125. So again, we use our calculator. That gives us 7.5 litres. Okay. Part B then. We're asked to work out the distance the car travels when it uses 5.7 litres. So our 5.7 litres is equal to 0.06 times our distance. So we want to know the distance, so we're going to divide both sides by 0.06 to get our distance. And so our distance is 5.7 divided by 0.06, 95. And our units for distance this time, we're travelling in kilometres. So there we go. We've had a look at 3 very different questions. One that was very scaffolded to help us to work through it. One that was similar, but they'd taken all the scaffolding away and just asked the question. And a third one where they've not mentioned direct proportion at all. So we need to work out that that's what we're doing and follow through the process as well. All right, finally today then, we just want to have a look at what direct proportion graphs look like. So here we've got a table of values. Again, we're using pounds, this time with dollars. So if I have no pounds, I have no dollars. If I have £1, then I have $1.20, £2, $2.40, etc. Now, if we were to plot this onto a graph, it would look like this. So our pounds and our dollars. So we can see that our graph of direct proportion, pounds and dollars are in direct proportion. Every £1 I go up gets me an extra $1.20. we get a straight line, and it's a straight line that goes through 0, 0. So when two quantities are in direct proportion, the graph is a straight line that goes through 0, 0. So remember, anything in a green box is important and a good idea to write that down in your book. So perfect straight line through 0, 0. Okay, a final check then. So which of these shows direct proportion? So have a look, have a think about what we've just said. Which of those would be direct proportion? Okay, so looking at the first one then, we have got a nice straight line here. Okay, but it does not start at 0, 0. So the first one is not in direct proportion. Our second one, again, a nice straight line. We're doing time and distance here. It does start at 0, 0. That one is in direct proportion. A conversion graph for gallons and litres. So again, nice straight line. Checking it starts at 0, 0. So yes, again, direct proportion. And our last one, we've got time in years against the amount of money in an investment. Doesn't start at 0, 0 and is not a straight line, so very clearly not a direct proportion graph. So you should be able to recognize whether a graph is showing you direct proportion or not. So the key points, straight line and going through 0, 0. Okay, well, thank you for working through that today. If you need to, do go back and check through any of those key points again before next lesson. Next lesson, we'll be having a look at inverse proportion.